Mm, you and field.
Realize he appreciates you, loves you, respects you. When you start dating an older man, TikTok. Good afternoon. So this is for my couples out there. Okay, this is my first video. This is for my couples out there, men and women. Speaking of you ought to know, since we're celebrating Jagged Little. That time of the year is the Sephora.
Mm. How's it going, Matt?
How you doing?
All right. I was just starting to worry that people weren't coming or that I'd cancel class by accident.
No.
Well, maybe I sent an email to the wrong people. How's it going, Jack?
Going all right. Got food in my mouth right now. That's why I'm not responding.
From y'all can ask any questions you want. I'm hopefully we can wait a few minutes to get some more people in here, but we'll have to start up pretty soon. We're going ahead and finishing out chapter 31 today. I've already shown you sort of how well, I've shown you Maxwell's equations, and I've shown you how Maxwell corrected Ampere's law. And we're going to do one application where we apply that, and then I'm going to what I'm going to do next. So I'm going to derive a relationship for basically a wave equation, so we can determine some stuff about the electromagnetic radiation. What we know of is electromagnetic radiation, but they weren't really sure what it was at the time of Maxwell. But Maxwell was able to work that out and derived a wave equation. So we're going to do something like that. And then I'm going to introduce a Poynting vector, which is a quantity that allows us to find not only the energy per second per square meter, the energy intensity that electromagnetic radiation brings, but you can even calculate the pressure that radiation can cause. So for instance, you can imagine a solar sail on a spaceship, so like a sailboat, but in space, where the sail actually is pushed by like the solar wind or just actual photons. So we're going to do that, and that'll pretty much finish up this chapter.
So, Professor, for this chapter, the homework is due in a week, right? We're a little bit behind on the homework to class thing.
Yeah, let me double check that. I think I set it up properly.
It is, but I just want to make sure so I don't roll around on Monday and be like, oh crap, I have 2 assignments due.
I'm looking at it right now. So yeah, I'm on the right class too. That helps. I looked as far as I thought I saw 241 instead of 242. I was like, oh crap, I'm on the wrong one. But no, I am on the right one. So 31, chapter 31. Yeah, I've given you like a whole extra week. So 11:14 is when 31, chapter 31 conceptuals due. Chapter 31 homework's also due on 11:14. So you got plenty of time. I would not wait, because it's of course really difficult to do the problems long after we've covered the material. Luckily, I'll have it, the advantage of having the videos posted usually within the day, if not the next day. So that won't hurt you quite as bad. It looks like it's going to be us 3, though. Nathan's here now, so I guess we should go ahead and get started. Just again, anybody have any questions? I know I dropped the ball. I had a death in the family, and my wife and I drove out to West Virginia to see some of her friends and family and spend some time with them and go to memorial service and all that stuff. I knew I had told you guys I was going to set up another practice final. I'm still going to do that. At just everything's got pushed back by about a week. So I'm going to do that. I haven't forgotten. It's just a matter of it being a little bit swamped with, 12-hour drives and whatnot. So anyways, we'll go ahead and I'll go ahead and fix that over the weekend. If you don't see it Monday, remind me, because then I really probably forgot it. And that's just me. So no questions from anyone? All right, well, I'm going to start off with an application of the correction to Ampere's law. So remember, we did Ampere's law, which originally said the closed integral of B dot dl is equal to mu 0 I enclosed, where basically you could imagine any complete path that completed a circuit. In other words, like a rope, say, that started at one point and ended at the exact same point. So you literally take a length of rope and you glue the ends together so that they're touching. Now you put that rope in any shape you want, and then you're going to do an integral around that rope in a particular direction, right? Well, what Ampere's law tells you is that the line integral of the magnetic field along that closed loop is equal to the current that actually penetrates any surface that is bound by that rope. So you can imagine now, I like to use this analogy. So you can take, for instance, a little vat that's big enough to hold your rope in whatever shape you want. Take a little vat, maybe that deep, and you fill it up with mostly water and then some dish detergent and then some glycerin. And that's called bubble solution. That's basically what you used to do when you were a kid, when you made bubbles, is you mix glycerin, or you'd buy a bottle of it and it'd have some glycerin in there, it'd have some soap in there, and then it would have water. And if you up the glycerin and the soap, you could make, pretty strong ones, sometimes too strong. So you have to play with the mixture a little bit. But if you take that rope now, whatever shape you want, let's bend it and let's pretend like it's actually like a bendable French square, or excuse me, a bendable French curve. So they actually sell those, by the way. I have like 3 of them. But imagine it's like that. So you can bend the rope in whatever shape you want. Now you dip that rope, which I'm assuming is going to be planar. It doesn't have to be, but in principle, it normally is. So you dip that rope in the actual bubble solution, and you get it nice and saturated. If you pull it out really slow, what you'll get is just a flat bubble spanning the whole range of the actual rope. Okay. But if you give that a little pull through the air like that, then it'll bulge out and make all sorts of shapes. And you can, bulge like this and do like that. So it'll actually make like weird shapes. Well, any of those bubble shapes that you can actually make are fair game to use to attach to that rope. And any current that goes through any one of those shapes has to be counted. But as I showed you, if you actually put that rope around a wire, then that flat plane of bubbles has the current go through it. But if you use like a sack, then that sack going between the plates of a parallel plate capacitor has no current going through it whatsoever, in which case you don't get the integral of B dot DL being anything other than 0. And that's what Maxwell saw. So Maxwell, I showed you that basically you can just assume that you're going to make something with the units of current, and that's the units of charge per time. So if you take the derivative of the charge of a capacitor with respect to time, parallel plate capacitor, you end up getting exactly the right formula. That turned out to be the displacement current, which again, the name was based on a since discarded theory. So it doesn't mean that much now as far as when you say displacement current, but that's still the name we use for it. But don't try to put much stock in the meaning of the word displacement in that sense. So what I'm going to do now is I'm going to do just that. I'm going to actually solve a problem in which we have to employ the displacement current to calculate something. Specifically, I'm going to take a round parallel plate capacitor. I'm going to connect it to a resistor and to a battery. And the instant I connect it to a battery, what's going to happen is the current is going to start off at its maximum, because initially the current doesn't see the capacitor as a problem whatsoever, because just as quick as it can send a positive charge, which, conventional current is pretending that positive charges are leaving the positive side of the battery. So as soon as you connect it, positive charges are running around the wire, going through the resistor, and then they get to the parallel plate capacitor, and instantly they start stacking up on the positive plate, but they instantly cause the positive charges in the negative plate to run away. So the battery really doesn't know anything's different. So initially the current is, it's maximum, but it immediately starts to decrease, because as more and more charge builds up, that gets harder and harder to do. So initially it just acts like it's going through a resistor. So when we do that, what we're realizing is that the current is going to be going up at the same time, or as a result of the change in current and charge building up on the parallel plate capacitor. And we're going to try to calculate what the magnetic field induced between the plates of that parallel plate capacitor are, and then realizing that parallel plate capacitors pretty much have very little electric field extending beyond the edges, because there's some fringing effects. You do get some, but we're going to assume that the electric field is essentially 0 out there, and calculate the magnetic field induced both between the plates as well as outside the plates. And lo and behold, it'll give you the exact same result as what's around the wire. So that's kind of cool. So let's do that. I'm going to start by sharing my screen. And hopefully you guys can read cursive. If you can't, it's not a big deal. I'm reading it out to you. So, but I did write everything in cursive because it takes so long to write if you actually have to write in script. So let's see. Okay, so there it is. It says a round parallel plate capacitor has a radius of R equal 5.642 centimeters and a capacitance of C equals 50.0 picofarads. Remember, pico is 10 to the negative 12. It is connected in series with a 5 ohm resistor and a 100-volt battery, 100.0 volt battery. When the battery is first connected, the current is a maximum and the electric flux change is also a maximum. A, calculate the current at that time. B, calculate the rate of change of the electric flux and the rate of change of the electric field at that time. C, determine the magnetic field induced between the plates. D, determine the magnetic field induced for R greater than big R as well. So in the first part, in part C, we're actually determining it for R less than big R. And then this part D, we're determining it for R bigger than DR. Or excuse me, R bigger than big R. Okay, so what we're going to make use of is a result that we did earlier. I think it was maybe chapter 28. I can't remember really, but we're going to make use of the charging of a capacitor. So our solution, I'm going to write up in red. Okay, our solution is going to make use of the fact that Q of T is equal to C times V times 1 minus E to the negative T over RC. The reason why I'm going to make use of that is that's the actual charge going through the capacitor, going through the circuit, i.e., and landing on the capacitor as a function of time. And in part A, they want us to calculate the current at that time. So the current is going to be dq dt, and we can calculate it accordingly. So let's start with part A. So I of T is equal to dq of T over dt. Okay, well, you can see that the CV, when I distribute that CV, the first term is just CV, and that's not a function of time. So the derivative of that term is going to be 0. But I will be left with negative CV times d by dt of e to the negative t over RC. And of course, the derivative of e to the negative t over RC is just e to the negative t over RC times the derivative of negative t over RC with respect to time. So that's going to make this become a positive CV over CR, which I'm obviously changing the order of RC for reasons that you can tell. And then what's left is times e to the negative t over RC. So now you can see that the C's cancel out like that, and I just get V over R times e to the negative t over RC. So that I of t equals 0 is just V over R. Switching back to red, just to keep things spicy, I get I is equal to 100.0 volts over 5.00 ohms, which is 20.0 amps. So that's all I can fit on the bottom of this page, but I'm surprised I was able to fit that, so I feel okay. So that's the actual part A, calculate the current at that time. So the current at that time was in fact 20.0 amps. Anybody have any questions on that? All right, part B wants us to calculate the rate of change of the electric flux and the rate of change of the electric field at that time. And then C wants us to determine the magnetic field. So let's go ahead and calculate the rate of change of flux and all that good stuff. So what we do know is that C is equal to epsilon 0 A over D. And we know A, since it's circular, is going to be pi R squared. So A is actually going to be pi times 5.642 centimeters squared, which lo and behold turns out to be 100.0 square centimeters. And then of course, A technically needs to be in square meters. So A is equal to 100.0 centimeters squared times 100 centimeters in the bottom. is exactly equal to 1 meter in the top. So I got to square that to cancel out the two of them. So that gives me 0.01000 meters squared to the proper number sig figs. But we also know that C is equal to 50.0 times 10 to the negative 12th, because it's picofarads. Capacitance is 50.0 times 10 to the negative 14. So what we're asked to do in part B is calculate. This is a horrible looking B here. I'm angry with it. Okay. So what we're asked to do in part B is calculate the rate of change of the electric flux. Well, the rate of change of the electric flux and the rate of change of the electric field. Well, the flux electric is equal to the integral of E dot dA. Okay. Now, the electric field really isn't changing. In fact, if we looked at it, it would just be, if we looked at the face of the positive plate, we'd basically just see electric field lines pointing straight out at us. Okay. And that electric field is actually uniform. In fact, we know exactly what that electric field is. It's going to be equal to the integral of sigma over epsilon naught, let's say in the k hat direction, dotted with dA in the k hat direction, which obviously gives us sigma over epsilon naught times A. Okay, so that's what the flux is. So if I want to calculate the change in the electric field or the change in flux, I need to use that. Now, what we also can realize is that the electric field, the sigma that's given there, is actually charge per unit area. So I could actually write this as sigma, or excuse me, I can erase that sigma. I can write this as Q over epsilon naught times A is the electric field, and then that times A there. So I'm going to mark this off so I can remember, hey, that's E when I want to calculate the the rate of change of the electric field. And then obviously the rate of change of the flux would be the derivative of all this. So let's first off do the rate of change of E. So the rate of change of E is d by dt of Q over epsilon naught times A. That's equal to 1 over epsilon naught times A times dq dt. Okay. And obviously, that is just equal to basically I over epsilon naught times A. So that's the rate of change of E. So I will write this now in red. dE over dt is equal to I over epsilon naught times A. That's one result. And we can also write that the d phi E over dt is equal to, of course, d by dt of Q over epsilon naught A times A, because that's the whole flux, right? So in this case, the A's actually cancel out, and I just get 1 over epsilon 0 dq dt. So this is just I over epsilon 0. So I can say d, well, actually I should do that in red. G electric flux over dt is equal to I over epsilon 0. And of course, we need to figure out what that I is. Well, that's okay. We know that Q, so I'll go back to red, Q is equal to CV 1 minus E to the negative T over RC. And we've already computed that down here. Remember, we got basically dq dt is equal to v over r times e to the negative t over rc. So that gives us dq dt evaluated at t equals 0 was equal to 20.0 amps. So I can say dE dt evaluated at t equals 0 is equal to 20.0 amps divided by 8.85 times 10 to the negative 12th coulomb squared per Newton meters squared times the area, which is 0.01000 meters squared. Notice that meter squared cancels out, and ultimately get, calculating this is dE dt. I think I got 2.2599. 2.2599. Obviously, that's 2 extra sig figs times 10 to the 14th. That's a whole lot now. And that's volts per meter, which is the units of the electric field per second. So that's actually the numerical value we would want for dE dt. Now, if we want d phi e, if we want d, whoa, got back to my eraser again. I hate it when it does that. What we found d phi e over dt was, and this is evaluated at t equals 0, was just plain I over epsilon naught. So that's going to be 20.0 amps over 8.85 times 10 to the negative 12th coulomb squared per Newton meter squared, like such. And obviously, this dE dt was basically the same thing as this, except multiplied by 100. So this one's going to be divided by 100. So it'd be 2.2599 times 10 to the, since we're dividing by 100 now, it's 10 to the 12th volts per meter per second. Actually, you might even try this. Oh, that could be. Remember, the units of the electric field are technically volts per meter, meter squared per second. Volts per meter times meter squared being the flux, and this would be per second. So ultimately, that actually gives you just like a unit of volts meters per second. Any questions on that? All right, so that was part B. Now, part C, they wanted to know the electric field, the induced magnetic field, both for R less than big R and for R greater than big R. So I've got to do a little bit of thinking about that to sort of make sense of Ampere's law. So C says determine the magnetic field induced between the plates. That means for R less than big R, where big R is the radius of the parallel plate capacitor. And then D says the same thing for R greater than big R. So when we do that, it's not too bad. So let's start off with C. What we have is the left-hand side of Ampere's law, the closed integral B dot dl. Now here's the problem. Okay, this is not a current. We don't, there's no current. We've worked Ampere's law before when Ampere's law was, let me write it up here. The closed integral B dot dl is equal to mu 0 I enclosed. But right now we have I enclosed equals 0, but we do have plus mu 0 epsilon 0 d by dt of the changing of the flux. Okay. Now, if we look at the plate, so let's say we look at the positive plate, and I'm going to look at it a little bit of a skewed angle. So let's say we're looking at the plate. What we know is the wire comes in perpendicular to the plate, And then the magnetic field lines stick out perpendicular to the plate. So these are E. And it's actually a uniform electric field. We know that. So notice the electric field lines point in the same direction as sort of the current would. So by the symmetry of that, we would suspect if I sort of made, let's say I make this the x-axis and make this the y-axis, both of those being in the plane of the disc of the plate, and this being the z-axis, then it looks to me, according to the right-hand rule, if that was a current I as opposed to an electric field, I would put my thumb in the direction of the electric field and curl my right hands around it, and that would be in the theta hat direction. So my hypothesis is B is equal to B of R times theta hat. Okay. And then, of course, the electric field obviously is in the K hat direction, and that should make sense. So what I'm going to do now is I'm going to imagine a Amperian loop going around in this direction like this. And notice it's at R less than big R because it's smaller than the plate. And I now get, from this Amperian loop, I'm going to get 2 pi r times b of r, like we always do. And again, the reason is that this integral becomes, whoa. I hate it when this thing erases stuff at random. This integral is going to become b of r theta hat dotted with r d theta hat, and that's going to be integrated from 0 to 2 pi. So that's why we're going to get 2 pi r d theta. Does that make sense to everyone? Now I can take the right hand side. Anybody have any questions about that left hand side? See how we use sort of the symmetry of what we'd studied before and how I behaved versus how B behaves. And now we're looking at how E behaves to see how that's going to create a B. So it's kind of this neat symmetry that the current creates a magnetic field that wraps around it, but the electric field creates a magnetic field that wraps around it as long as the electric field is changing. So the right-hand side is mu 0 I enclosed plus mu 0 epsilon 0 d phi E over dt. And as we said before, that's 0. So this just becomes mu 0 epsilon 0 times d phi E over dt, which now we can't say the full 20 amps. We have to say, we have to figure out what fraction of the flux is going through. So in fact, the flux is now going to be, again, d by dt of the flux is going to be A times E. So that's going to be mu 0 epsilon 0 times pi times r squared, because the A is not going to change, and it's just going to be a radius r for whatever radius we choose at that particular instance. We just know r is less than big R. And then we're going to have a derivative of E with respect to time, because also the orientation of the A vector with the E, which both point in the K hat direction, that's not going to change either. So that derivative doesn't make any difference. So I'm just left with times dE dt. And what we found dE dt was dq over dt over epsilon naught a. Okay, where a was, of course, the parallel plate radius, or excuse me, the parallel plate area. So this is all for part C. Now, if we stick all this together, left-hand side equals right-hand side. I'm going to use some blue to break this monotony up. I'm going to get 2 pi r, put it back in red, 2 pi r b of r is equal to mu 0. Notice bare minimum, the epsilon zeros cancel out. I'm still thinking about what's going on with that a down there. Okay. Okay, yeah, that a has to be the whole a. So that sorry, I was just working that out in my head just to make sure. So anyways, this is going to be times, stupid me, wrong color, times pi r squared times dq dt, which is, we can call it I if we wanted. I think I'll go ahead and call it I, and I'll leave it as dq dt. What the heck? So that's dq dt over a for the capacitor. So I'm not even going to put in any junk about the pi r squared and all that stuff. You can see what it would be. It'd be pi times big R squared, which ultimately just comes 0.01000 square meters. The main thing is right here, I can see that this pi cancels out with this pi, and this R cancels out with one of these R's. And I ultimately get that B of R, or excuse me, B vector, is in fact going to be equal to, depending on how I wish to write it, it's going to be equal to mu 0 over 2 times A of the capacitor times dq dt times r in the theta hat direction. Okay, now if I want to compute all that stuff, it's really not that bad. I can also, and I'll write it here, I've already done the math of it, and what you get is B is equal to 1.257, carrying one extra sig fig, times 10 to the negative. Now I'm trying to remember if I did this right. I think I got 10 to the negative 5th. Anybody want to verify that calculation for me? Because I have this something weird written in my notes, but it's Tesla per meter times R theta hat. And what I'm not sure about is I have 0.01257, and then I have times 10 to the negative third. I can't imagine I'd put something with some value other than that. Where am I at now? I just changed everything. Okay, there it is. I can't imagine I would have put that. So let me just do the calculation real quick just to make sure. So what I said was 4 times 3.14159 times 1 e to the negative 7 times the current, which would have been 20. And now I'm going to divide that by parenthesis 2 times 0.01. Remember that 0.01000 technically, because the sig figs. And I think that's it. So close parenthesis. Oh, yeah, so it's supposed to just be 1.257 times 10 to the negative third, not 10 to the negative fifth. So yeah, I've got it written correctly. So I'm going to box this off too. So this is the numerical form of it. So all I had to do is if I want to take a certain distance, and this is for R less than big R. If I wanted to take a certain distance R, I just have to multiply it by that 1.257 and make sure the R is in meters, and that will give me the magnetic field strength at that particular R less than big R. Does that make sense to everyone? Any questions on that? Okay, so that's part C. Now part D is pretty much the same thing. We're still going to get the same left-hand side. We're going to get 2 pi R times B of R. We're going to make the same hypothesis that B is equal to B of R times theta hat. The right-hand side is going to be more or less the same thing, except the area, or excuse me, except the mu 0 epsilon 0 times pi r squared is just going to be the area where the magnetic field is not 0, and that's only for R less than or equal to big R. So it's only going to go out to big R, and of course you can see that's even going to cancel out with the A down at the other side. So let's go ahead and do, starting from there, we're going to say here's part D. This is for R greater than big R. And what we see is left-hand side equals right-hand side is just going to give us 2 pi R B of R is equal to mu 0 epsilon 0 times pi big R squared. And what we found before was we had 1 over epsilon 0 times pi big R squared again times dq dt. And you can see now that basically that power squared cancels out with that power squared, that epsilon 0 cancels out with that epsilon 0. And this right here is really convenient to call it I. And I think you can now see why, because in fact, what we get is B is equal to, all we have left on the top is mu 0 and I, and all we have left on the bottom is 2 pi R. So you see that we got exactly the same formula that we got when we did Ampere's law for the enclosed current at the wire part. So I can actually work out the mathematics of this, and I did. It turns out to be 4.00 times 10 to the negative 6. And that's Tesla meters over R times theta hat. So all you have to do now is put in an R down there at the bottom that happens to be in meters, and it'll automatically spit out the magnitude of the magnetic field. And again, this is for R greater than big R. If you'll notice, the actual magnetic field is continuous, and we can sort of see the same graph we did before when we did this for a wire. If this is R and this is B, this is going to be mu 0 I over 2 pi big R, and this is big R. So we'll have a linear function to there, and then it'll fall off like 1 over R there. And in fact, the max magnetic field that you get is mu 0 I over 2 pi R. So if we want to, we can see that that quantity right there, mu 0 I over 2 pi big R, is actually equal to, I want to say 4 times 10 to the negative 6. And I'm going to divide that by 0.05642, which is the radius. I think that was what the radius was. Yeah, 0.05642 meters. And that gives me 7.09 times 10 to the negative 1, 2, 3, 4, 5, 10 to the negative 5th Tesla. So that's the maximum current that we actually get, or excuse me, the maximum magnetic field that we actually get as a result of this. Remember, I've mentioned this to you before, but the unit we chose in an Earth-like manner for the magnetic field is a huge unit. So oddly enough, like when you look at electromagnetic waves, you see the electric field oscillating in one direction, magnetic field oscillating in another, but the electric field will be huge compared to the magnitude of the magnetic field. But that's just because the units, it's not good to think about it that way. So anyway, anyone have any questions about that now? Alexa, turn off music, please. Evidently, she interpreted me saying something as telling her to turn on some music. I'm going to correct that now. All right, so no questions on that. Everybody feels pretty good about that. All right, so now what I'm going to do is I've hinted to you guys about what the electromagnetic field or electromagnetic radiation looks like. And basically what we found out was that there is electromagnetic radiation. Maxwell, if you look at my YouTube video, I actually did that with the vector calculus method of deriving an equation, a wave equation for the electric and magnetic field. And when Maxwell did that thing, he found out that in the spot of the classic wave equation, which everybody in physics knows, a wave equation is basically a second order derivative in space is equal to 1 over the velocity of the wave squared times the second order derivative of the thing that's oscillating with respect to time. That's the main wave equation. Well, when he looked at it, that equation, he saw in the slot for V was 1 over the square root of epsilon 0 times mu 0. So both of those were under the square root and in the denominator. And in fact, if you multiply those two numbers, take the square root of them and then flip it over, you get 2.9979248 times 10 to the 8th. That happens to be the speed of light. So at that instant, Maxwell knew, oh, wow, this is what light is. I know what light is. And what he found it is, and you can do this from those equations, just put them together algebraically. Light turns out, I'm going to stop sharing for a split second just so I can explain this to you. So light turns out to be electric field oscillating in one direction, let's say up. And if it's oscillating up and down, that's called vertically polarized. So when you hear about polarized sunglasses and all that stuff, that's what that word polarization means. Polarizing means which the electric field has a specific direction. And in this case, it's going to be vertical. So the electric field is oscillating up and down. The magnetic field is oscillating perpendicularly to that, and the velocity is perpendicular to both. So what we find is that if the electric field is oscillating up and down, when it goes up, the magnetic field is going to the right, and when it goes down, the magnetic field is going to the left. So I know I've gotten completely off vertical with that, but anyways, and then the velocity would be straight ahead according to a right-hand rule. So you can say, let's treat the index finger as E, let's treat the middle finger as B, and then let's treat the thumb as velocity, and you see that that's what's coming at you. So what does that look like? Well, let me show you what it looks like. Now I'm going to go back and share screen so that I can show you what it looks like. And I think I've drawn this for you before, probably a couple of times, in fact. I know I've drawn it for a bunch of students, even drew it in one of my labs that was unrelated. So what we're going to look at is we're going to imagine a line that's coming out of the screen here. and that's going to be the direction of the velocity. Okay. I'm going to imagine an electric field looking like, let's say, looking like a sine wave. Okay. And then I'm going to imagine the magnetic field looking like a sine wave perpendicular to it. Okay. And this means the electric field strength right here is this, and here it's this, and here it's this, and here it's this. And the magnetic field strength here is this, and this, and this. And the velocity, like I said, V is equal in magnitude to C. And C equals exactly 299,792,458.0 with a bar over it meters per second, which also happens to be 86,100 miles per second. And it also happens to be like 34 million, maybe it's 341 million miles per hour. So that's some other values. So that's what the actual electric field is. And the plane in which that's what the electromagnetic radiation is. That's what light is. And that's what all of what we call the electromagnetic spectrum is. So the electromagnetic spectrum, I will give you a mnemonic for that. And actually, I really should. Can one of y'all request a transcript be made? I don't know if I can do that from here. Do y'all know how to do that? It's a highly helpful thing. There it is, live transcript. Enable. Okay, so I think I did it now. So there should be a live transcript being made, but the mnemonic I use is sort of an ode to Rush Limbaugh, who recently died. I've been paying attention to his television show initially, and then his radio show after that since 1988. I started watching the show in '88. So never mind what my position is on the politics of him, but I've just enjoyed talking about politics and listening to politics and stuff like that all this time. But one of the things he always said is that teachers are commie pinko bastards, basically. So so I made a mnemonic for the electromagnetic spectrum, and pay attention to the letters I write and the words that I say, but it's basically great excess. Notice I'm spelling excess with an X. Okay, great excess undermines various industries, Marxism rules. Okay, so anybody want to guess what type of radiation G is? I'll give you a hint. Incredible Hulk.
Gamma.
Yep. And how about the X? I broke my bottom.
X-ray.
Yep. And the U?
I don't know.
That one's ultraviolet. So that's a sunburn. How about the V? I see.
Visible.
Yep. Now on the end, that end of the V is the red. So what do you think the I is?
Infrared.
And how about hot pockets?
High frequency.
The M is microwave. So the R, anybody want to guess what that one is?
Radio.
Radio, that's right. Okay. And now the downside of this is you can't use Roy G. Biv with this mnemonic. It actually has to be Vib Gior. Okay. But that makes sense, right? Because violet should be next to ultraviolet and red should be next to infrared. And in fact, this is actually a very small area. This end, the left end, is about 350 nanometers long, and the right end is about 750 nanometers long. Okay. And in fact, the order is high frequency to low frequency. And if you realize that velocity of a wave is equal to frequency times wavelength, and all of these waves have exactly the same velocity, namely the speed of light, then you see that if f goes up by a factor of 2, what does lambda have to do? So if the frequency goes up by a factor of 2, it goes from 100 hertz to 200 hertz. What's going to happen to the wavelength?
It has to happen.
It goes in half, exactly. So you see the f and lambda are inversely related. So this end is low wavelength, this end is high wavelength. There also happens to be something called Wien's law that basically says the temperature is inversely related to the wavelength. So low wavelength means high temperature and high energy.
Are you sure that Bean is spelled right?
Yeah, it is actually a W, but we pronounce it with a V. And it's unless
Are you
think,
sure it's EI, not IE?
Gotcha. Yeah, that might be right. But I do think it's EI.
So
It is a
I'm
German
betting
word.
that his name comes from Vienna, which is, of course, in English, VIE, but in German would be WIE.
I gotcha. I could be wrong. I will leave it for the Google machine and you guys to figure out, and that's fine. But yeah, that's what I think I remember his name to be, and it should be pronounced like a V, and he is from Germany, if that helps you. So that's low temperature on this side, and that's low energy on this side. So it's like Jeb Bush over here, I think is what they said. So that's the parts of the electromagnetic spectrum. And as we said, they're gamma, X-ray, ultraviolet, visible, infrared, microwave, and radio waves. And now what I'm going to do is, I've got a little bit of time, I'm going to try to make use of this wave this way. So let's kill this. And I'm going to use my equations that I know. So what I'm going to do is I'm going to draw first off the electromagnetic port, or the electric portion of the electromagnetic radiation. And now I'm going to draw the magnetic portion. Notice they are in phase. That's something important to realize. And what I'm going to do is I'm going to draw a little rectangular box. And I'm going to say, this is my x-axis, this is my y-axis, and this is my z-axis. And I'm going to draw another little rectangular box here. Now, both of those widths of those boxes are dx. This height is delta y, and this height is delta z. And the blue is the E field, and the red is the magnetic field. And if we use the closed integral of E dot dA, actually, no, I don't want to use that one. If I use the closed integral of E dot dL, and we don't have a current, then I know that it's mu 0 epsilon 0 d phi E over dt. And if I use integral B dot, ooh, that's the wrong one. Put the wrong side on there. This is Faraday's law, so it should be negative d phi B over dt. Sorry about that. And this side over here is B dot dl. And that is going to be mu 0 epsilon 0 d phi E over dt. So if you do the left-hand side here, so let's say left-hand side of that guy, what I'm going to get is I'm going to go around in a certain direction. I should indicate that. and indicate that way. So you can see which way I'm going around. So that leftmost one is going to give me a negative E times delta Y plus
I lost audio. I don't know if anybody else lost audio, but I can't hear you.
I see it muted. Sorry about that. I don't know how that did it, but I just looked up and it said mute. So did you get any of the equation stuff I was telling you? You got my audio now? Yeah.
I think I lost you right around when you started writing in blue.
Okay, gotcha. All right, so I don't know how that happened, but either way, what I was doing was the left-hand side of Faraday's law, and the left-hand side is where I'm calling it X, and that's E and B. And if I move a little bit to the right, that's going to increase to E plus DE and B plus DB. Okay, so in doing the line integral, I got basically E times delta Y times a negative, because notice the arrow points down on the circuit, but the electric field points up. So that's why I got a negative E delta Y. And then the other side, I got a positive E plus DE times delta Y. Now, when I distribute those delta Y's, you see that the E delta Y and the negative E delta Y cancel out, and all I'm left with is actually a positive DE times delta Y. Similarly, when I did the same cycle, but for the magnetic field at the left side is B, and the magnetic field at the right side is B plus DB. Now that equation for the left-hand side is supposed to be d phi B over dt. So I'm actually attempting to calculate the actual magnetic flux. So, oh man, I didn't mean to do that. Okay. So maybe I can erase this here. Okay. So what that is just the actually I should do the flux. Stupid me. So the flux through that is what I'm really trying to calculate, and I don't know. I slipped off and started doing the other part. Okay, so the flux through that is going to be just basically B times delta X times delta Y. So that's just B times delta, or actually we called that dx, didn't we? So that's dx times delta Y. And then of course that divided by dt. That's d phi B over dt, right? So if I set these two equal to each other, what I get is left-hand side equals right-hand side. I get dE delta Y is equal to negative B dx delta Y over dt. So what this does is I can cancel out the delta Y's, and I end up getting, going back to blue, dE over dx is equal to dB dt. oops, I forgot to put the D in front of the B. So that's equal to negative dB dt. Okay, that D was supposed to be there and there. So that's one of the type of equations I get. Now, if I do the same thing to that other rectangle that's in the red field and apply the right equation, I get left-hand side for the red equation. That's going to give me what I told you before. That's B times delta Z minus B plus dB times delta Z. That's the left-hand side. The right-hand side is supposed to be mu 0 epsilon 0 d by dt of the flux. So the flux through that is going to be actually E times delta x or dx times delta z. So I can actually set these two equal. You notice the B delta Z minus B delta Z minus dB delta Z, that ultimately gives us, going back to red, left-hand side equals right-hand side. That gives me negative B delta Z, actually negative dB, is equal to, now we're going to have mu 0 epsilon 0 dE over dt dx delta Z, sorry. Again, the delta Z's cancel out. And this gives me negative dB dx is equal to mu 0 epsilon 0 dE dt. Now, in principle, you can tell these electric fields and magnetic fields are not functions of just E or just X or just T. In fact, they're supposed to be in functions of X and T. So in fact, this equation becomes, writing in red, partial of B with respect to X is equal to negative mu 0 epsilon 0 partial of E with respect to T. And similarly, this guy up here becomes the partial of E with respect to X is equal to negative partial of B with respect to T. Now, you can actually set this up by, if you now take the derivative of the top equation with respect to, let's say, time, then you get the second derivative of B with respect to time with respect to X. But on the right-hand side, you get negative mu 0 epsilon 0 second derivative of E with respect to time. So if I do that, I can get second derivative of B with respect to time with respect to X is actually negative mu 0 epsilon 0 second derivative of E with respect to time squared. And now if I do the same thing with the second equation by taking the derivative of it with respect to X, then I'm going to get negative second partial of B with respect to X with respect to T. And by the way, you're allowed to flip the order of those, so it doesn't matter. And that's equal to the second partial of E with respect to X squared. So you can combine these two and see that you get the second partial of E with respect to X squared is equal to, notice this is a negative because it came from that other side, and that's equal to a negative as well of mu 0 epsilon 0 second partial of E with respect to T squared. So you get that the second partial of E with respect to X squared is equal to 1 over the square root mu 0 epsilon 0 squared second partial of E with respect to t squared. That is, in fact, the wave equation. That's the classic wave equation. You got a derivative, a second order derivative in space, a second order derivative in time. And this slot down here is v squared. So immediately that tells us v is equal to 1 over the square root of mu 0 epsilon 0, like that. And actually I have to put it under 1 to make this correct, like that. Okay, well, that turns out to be exactly C. So that's our wave equation. That's how we got all that stuff. I actually ran over time by like 7 minutes. I didn't get to do the Poynting vector, but let me just tell you, the Poynting vector is S is equal to 1 over mu 0 times E cross B. I'd actually prepared to derive that, but I'm not going to be able to do it. And that also, that for the sun, for instance, at our upper atmosphere is 1,350 joules per second per square meter. So if the atmosphere is not taking up too much, then a square meter of solar panel, if it was 100% efficient, would give you 1,350 joules every second. They're normally about 10% efficient, so you get more like 135 joules every second. But again, you'd actually have to subtract a little bit because that's at the upper atmosphere. But that is exactly what the Poynting vector, Poynting, says. Oliver Heaviside and a guy by the last name of Poynting found it about the same time, but the Poynting guy got it published first, so he gets to name it. We also found out that pressure, I think, is supposed to be 2S over C. I'll put a question mark over that, but you'll need that equation too if you want to calculate pressure. So I'll put a question mark over it, but that's really all the topics we missed in chapter 31. The derivation that they did is pretty easy to follow for the Poynting vector. I'm sorry I didn't get to do it for you guys, but I think that should do it. Does anyone have any questions? Because you're free to go, but I'm just here to answer any questions you might have. Go ahead.
I just had a question about the makeup midterm you said was due by the end of next week.
Okay, so no. What I told people, you came in a little bit after everybody. I got about a week behind because of personal issues and stuff. So I'm going to try to make up the new practice midterm, and my intent is to put like one conceptual question and one work question per chapter in it. Maybe I'll make one conceptual and make one non-conceptual that's just problems. That way it'll be a little shorter and you'll get an equal treatment of each of the chapters. And I should put that up. If it's not up by Monday, that means I forgot it. So definitely look for it by Monday. And then what's going to happen is I'll give you at least 7 days with that before you actually have to take the redo of the midterm, but I'm probably going to give you more. So like probably I'll open it maybe on Wednesday, the new midterm, and you'll have until the following Wednesday to do it.
Well, that new test will be somewhat more accurate to what we should expect.
It's going to be, I wouldn't say accurate to what you should expect. It's going to be even in that it's going to cover each chapter with equal importance.
Okay.
I tried to gear the last one more towards the most recent stuff because that was the stuff I suspected you had less of a mastery of. So I was wanting to drill that in, but that wasn't necessarily how I made up the midterm.
Okay, thank you.
No problem. Like I said, I'm staying here till the last person leaves. You guys are welcome to split, but thanks for coming, everybody. AJ, do you have a question? AJ might not be here. Okay, so that looks good. All right, I'm going to say bye. Have a good one.